Great. Good afternoon, everybody. Sure you've all seen my title on the itinerary for today. It's actually not the full title. Obviously, after the launch, everybody knows what it's going to be about. Comma 4. Concept of shelves. It's quite interesting. You don't really see any other companies talking about this, but I think it's very important to share like what happened during like the process of getting into the device that we have now. I would like to see more companies do something like this. So 2 years ago, I also did a talk also about hardware, about manufacturing in our office. To recap that a little bit, because it's still quite interesting. I talked about like this general like flow of like how a product like comes to be and like gets into your hands, where we start from like a general like vibe of what the concept should be. We go into like first design stages, we prototype it, test to see what's broken with it, then moves to production once like the design is finalized, gets to the consumers, and then we do the repair stuff. So what I talked about last time was like, okay, so we get the PCBs in, we have like our own manufacturing line. It's actually a picture I took yesterday. So all the 3 axes that you guys have received are all built on this line you see over here. But we've recently been setting up the second line, which should be even faster. So hopefully the 4 axes will run off the line as quickly as possible. So you deposit solid paste, you put on the components, you make sure that everything looks correct, and then it goes into the assembly room where all the components are mounted onto the board, and then it goes into the testing rack that Deep and other people have talked about before. Okay, so that's a quick recap. Let's go back to this. So last time I really talked about like the second half. So now let's focus on the first half. We really start to dive into like how do we get from the concept into like the production design that you guys saw today. It always starts with a code name, which we call Misi, and some wildly optimistic thoughts. I don't know if you can read this, but it's January 14, 2023. George posted, okay, let's start with something called the comma mini. So it's supposed to be small. I think we achieved that. It's going to launch at CES 2024. I don't know if you checked your calendar lately, but almost achieved it. And really the concept back then was like build like the absolute bare minimum thing that we could buy, that we could build. That still gives you like 80% of the value of the main like 3X that we had back then. And we figured it would look somewhat like this. Like it would look like a stock LCAS camera, but maybe have it be like passively cooled. It wouldn't have a display because like we need to display like a stock LCAS systems don't have this. We wouldn't store any training data. We wouldn't upload it back, so it didn't get any LTE, so we could drop that. We thought like, oh, well, like Toyota back then was like half of the fleet, so maybe we just only support Toyota. We put like the Toyota connector on there. We increased the narrow road camera field of view to make sure that like you didn't need like a special mount for like the cars that have like the tilted windshield, and really like minimize all the production steps. Like if you think about it, it's like this is all it really needs to be, right? Like it's one like die-cast metal piece. You place on one PCB there. You have like the other PCB with the cameras on there. That's all you really need. And I don't know if you like if you go to this link, this is some other company designed this, and it looks so uncannily like the thing we came up with back then. It's crazy. But then we thought about it more, and like, well, having no display, I mean, that's really annoying, right? Like, how do you set it up? Like, how do you get this thing? You take it out of the box, you put it in your car. Like, you have to like connect it to Wi-Fi. Like, you can't input anything. There's no buttons. Like, you have to like make a good app. You have to like, support Android, support iOS. We're historically not very good at any of this. So we thought like, okay, let's just put a display on there. And from our experiences, like getting a custom OLED made, like in the shape that you want, that's basically impossible. Like if you're like a Samsung and you want to build like a Galaxy watch, all the stuff's very easy, right? Like you have like, you buy like 1 million of them, you spend like a few $1 million, everything works. That's just not really the scale we're at yet. On the other hand, LCDs, they're a little easier to like customize, but we've tried this before, but like in the 3X stages, like prototyping stages. This is actually a picture of that I pulled from our Slack, where you can see like, okay, we put this thing in an oven for a few hours. These LCD panels are really not made to like withstand like higher temperatures you would see on a car dashboard. And so this is also not really an option. But fortunately, we're looking around the markets, and we finally found a company that makes a very nice, tiny, little AMOLED display. It's almost the right form factor, right? You can imagine this is this height. It kind of matches the driver camera. The width is roughly what we would expect for the device we wanted to build. This is great. And the thing is, you don't even have you don't want it to be square, right? That doesn't really fit in any device. But if you can just replace the front glass, which is a lot easier to customize, you can actually make something that looks pretty nice. And so that's the thought that we went on a little further. Contrast isn't great. But I really had this concept of this thing, maybe we can make it look like a Mac Mini, with nice rounded corners, you have a nice rounded display. And it actually kind of looks like the comma 4 we ended up building. And thinking about it a little more, it's okay, if you already added back the display, why don't you just make it better than a 3X? If you just add back LTE, which can't be that hard, we add back OBDC, so we support all the cars. There's really no drawback in having this device versus a comma 3X. And instead of calling it a comma MISI, let's just skip that, comma 4. So just build a new flagship, that's great. You don't have to support 2 different product lines. This is gonna be amazing. So once you have this concept, that's all still in magic land. Everything looks great on a computer screen. Obviously it doesn't drive your car. So you want to get something driving as soon as possible. That also means that you have a product you can hand off to for example, the openpilot team, so they can start working on the UI. How does this thing look like in a car? Can I design an interface that works with this? Possibly, very well. And you can also test out different refactors you want to do in the electronics. And so this is something that we really thought about, and we really tried to optimize the first prototype to be driving as soon as possible. And most of the important things, one of the most important things to get something driving as soon as possible is you really have to select which processes you're going to use. You don't want to do anything fancy that would take months of lead time from different companies, or something that only one company in the whole world can do. You really want to stick to the basics, 3D printing for the case. Or if you want to do a metal case, you just have it CNC machined. That stuff is all super easy, and you can get it done in hours or days. The electronics, that's a little less easy than the mechanical parts to speed up, because if you want to put something like a Snapdragon 845 onto a PCB, you really can't do that on your standard JLC level 4-layer PCB. Which they produce in a week, but you really have to step up to an 8-layer board which has vias that don't run all the way through the board, go from for example layer 3 to layer 4. And these things they take weeks and weeks to produce. It's not even just production time. These things, they actually take 6 to 7 weeks to produce, but they also take 3 to 4 weeks to even just design and route out. You don't want to do 50 revisions doing this, because you'll just be stuck for years. And then for the other parts, if it's not broken, just don't fix it. Just take parts that already work. From, for example, the 3X, we already had a heatsink that worked, and just stick it on there. This is also the board that we designed for the 3X, which has the 845 already on it. So we figured oh, let's just reuse this module, get it on the first prototypes, and it'll be driving immediately. And that's exactly what we did. So from the time we started the design, we had PCBs ordered in 9 days, and then after 13 days after that, we had the first thing booting. And so that means that we could hand it off and get all the development teams start working on software, firmware, that kind of stuff. And only 3 days after that, we got the first one driving in a car. Now, I do say driving. It did drive, but the screen is still black. It's obviously prototypes make mistakes. The screen didn't come up. Every time we plugged in a screen, we see a puff of smoke, and be oh, something's not right. So the connector was mirrored. It happens. You only make this mistake once, right? You just design a small PCB. You don't want to respin that rigid flex board, because it also takes 2 weeks. You just make one simple 2-layer PCB. You get that in a few days. The display is up. Everybody's happy. So that's kind of what this board looked like. It worked. I posted it to Slack, and then in the same vein that Shane got the feedback from Adeep saying oh, this should only be 10 lines. This feedback was immediately, that looks like way too much stuff. I kind of agree. In the end product, you see now, like, at least 25% of the components that are on here are just removed, like refactored out completely. Like we got the STM to do like the audio codec stuff. We replaced the beeper with like just driving the beeper signal through the speakers, all the stuff that just you don't need. And you just reduce complexity massively this way. Okay, so we had the SOM prototype driving. I mean, that's obviously not something you can just refine on and ship. So we really had to think about, like, okay, what is this device going to look like in the end? And the main driving factor for that is, like, what is the case going to look like? Like, you can't design like this complex PCB and change the shape because all the components move and you have to move all the traces. That just, every time you do like an outline change, that takes like weeks to materialize. So we thought about it a little bit, and I like my Mac Mini design. There were other people in the company that didn't quite agree, and one morning I woke up and I got like this image. I don't know if you can see it very well, but it's just like Play-Doh mashed together into like a potato chip shape. And they were like, yeah, it needs to look organic. Like, oh, okay. So I came up with something that looked like this. I got really into like the fusion design tools to like make organic shapes and stuff. It's really nice. Igor, our mechanical designer, did not agree. So we completely threw that out of the window. And also, like, if you try to fit any components in this, like, the curves just don't really work. Like, anything you want to put in there is square. It just doesn't fit. And so like, we botched it out a little bit. And, like, you could kind of, like, start to lay out components. Like, we thought, like, okay, like, this is going to be, like, a nice die-cast aluminum case. It's going to be passively cooled. But like in some cases, you might want like a little bit of like active cooling, so we fit in like this blower fan to like get some air moving through the case. We laid out all the ports that we needed. We laid out the camera bar, the LTE module, the speaker, all that stuff. It kind of fit. And so after a few more iterations and design, we came up with this, which is the Rev A case. As you can see, like it's still like it's supposed to be made out of metal. It's still die-cast to like get the passive cooling working. You had like this big surface that would like the 845 would heatsink into, distribute out over the whole surface, and then would just like mostly cool itself passively and be quiet. We kind of proved this out as well. It's like I posted this on Slack a little after that, and I made like a very simple mock-up that we could simulate, where we dump in like the 6 watts or whatever the 845 outputs. And then it's like, okay, if you have like 25 C air, move up roughly 1.2 meters per second over the surface from like natural convection and like air currents moving in a car, this should just work. Turns out like both of these assumptions are completely wrong. There's no convection in a car. The forced cooling never hits the windshield. It's never 25 C. The air next to the windshield is so hot. This was completely off. But anyway, we didn't know that at the time, so we started laying out the Rev A. We put this nice big hole in the PCB where like the blower fan could sit on the other side. It could suck in air and then exit it through the top. That seemed like a good thing to do. We like had some trouble like laying out all the components on the board, but like it all kind of fit. We got it to work. We put that into like a flow simulation. Like, okay, it pulls air from the back. You can see like it moves like under the PCB, so it moves over the aluminum surface to cool. It pulls it up through the blower and shoots it out to the front. And like, that might work. And so we routed it out, we sent it out, and that was our Rev A of the MISI. Of course, as I talked about, this is already like the high complexity PCB, like a high density interconnect PCB, so it would take like 6 to 7 weeks to produce. And we didn't really want to wait on those 7 weeks before we could start stuff like mechanical design. So what we did is actually we just took the top and the bottom layers of the PCB, and we just sent it out as a 2-layer PCB. So it looks and functions exactly the same mechanically, but there's no traces in there. Like, it doesn't do anything. But it's still very useful, because mechanically it's completely equivalent. And you can get this in a week. We didn't make one mistake though. Usually the stuff that we intend to work, we make black, because that looks the nicest in the case. We figure like, if we want it to be mechanically equivalent, we'll also make this black. Turns out you just can't tell it apart from like a real PCB anymore. So I predicted back then, like how long is it gonna take before we're just gonna waste like half a day trying to figure out why this thing doesn't boot? And it didn't take very long. Okay, so once we got the real MISI Rev A PCBs in, It only took a few days. We got it to boot, so there was no like fundamental big issues, except like the cameras didn't work and the display was still black. We did it again. This time it was like just 180 degrees. So oh well. After fixing that though, just a few days later, we have the first actual drive of a MISI in a car. MISI Robbe, August 22nd, 2024. Okay, it's almost up and running. Like, it kind of drives. Like, we're nearly there. It will ship in like 2 months. It doesn't. Of course, Robbe, you make all these like tiny mistakes. We track this in GitHub. We have just make like a big list of all the things we want to improve for RevB. There's nothing too spectacular in there. Like looking at the thermals of that first drive, which you could have seen, like this was like the sun was already setting, it wasn't very hot out, it was like the car was like nicely cooled and AC'd. The thermals of the CPU, they just kept rising through the whole drive. Like it just didn't really perform passively like we thought it would. And so we thought like, okay, let's dive into the first principles, right? Like you have this 845 processor that we get from Qualcomm. That's soldered to a PCB, and then because it's usually used in a phone, they're very like space and power efficient to put the RAM like right on top of the chip. So it's actually like a chip you solder on top of another chip, which is great in phones where you have like very bursty loads. You don't really care about thermals all that much. But like with sustained loads of openpilot, this really limits like the thermal interface between like the die that actually produces most of the heat and like the heat sink you want to put on top of it. The 3X, we didn't optimize this all that much. Like what you basically have is just to put the heatsink on the top. It just mostly flows out of the top, and it's like mostly fine. But then we also figured out like this PCB is actually like 8 layers of copper in there. There's a lot of interconnects, so it's actually like thermally decently conductive. So what if you just also cool it from the bottom? Turns out that Qualcomm actually publishes pretty good high fidelity like thermal models of their chips. They can just simulate this. And turns out like you could get at least a third of the heat through the PCB out of the bottom. So that's already like an easy like 33% improvement that you just get for free if you design this in. We also validated this. So this is what we call the shot glass test. We just got a copper shot glass, filled it with water. And then if you run a constant load on the CPU, you can just like measure the difference between the CPU cores and the water temperature. If you diff those, you just get a flat line, and it gives you the exact temperature difference from this actual CPU die that you're trying to cool and the outside environment. And that's the best you can do in this setup. And it's like, it's still not really good enough. Like, is there anything else we can do? Like, you can see this like big air gap here, right? Like it's in between the balls, it's on the top of the processors, and like air, it's not very conductive. Everybody knows this. So what happens if you just add some epoxy in there that's like somewhat thermally conductive? It just fills all these gaps in, and it really improves thermals. Like this change alone, like improved thermals by at least like 1 C per watt, which is pretty massive in the things we've tried to optimize. And as an added bonus, because it's epoxy, it also like mechanically bonds the chips to the PCB, and that greatly improves reliability. So this is kind of what it looks like. So this is not a chip you're looking at. This was a chip. It's underfilled, and then you just mechanically like break it off, and you can see like the epoxy filled like all the empty space next to the pins. Another issue we found on the early MISIs is it's a metal case. If metal is at like 50 or 60 C, if you touch it, it's not good. It burns your fingers. The device is still running fine thermally, but like it doesn't really feel like a high quality product, and like it's just not something we wanted to ship. We tried to improve it. I made like this cyber MISI design, which I thought looked kind of cool. Like, the team wasn't very convinced either. But if anybody like wants to make this, I'll buy one. So we still have the metal case back there. And like this is also validated in the plots where like we didn't realize this, but a lot of the heat input actually doesn't come from the electronics inside, but it comes from just the sun like shining down onto the device. Like especially if you drive around in California or like the lower states in the US, you could see like one of these is case temperature. That's case temperature. It just keeps rising and rising and rising. It doesn't dissipate into the air. The case just gets way too hot. It's just not very good. We simulated this. So we made like a small little fake windshield with a device on it. We had like an IR heater that like we got to somewhat match the sun output, and we couldn't really get the metal case to work. So let's just cut our losses, let's just redesign it completely. And instead of dumping all the heat into the case, we know we can extract like 66% of the heat out of the top of the chip, which we could then put in like a nice heat pipe with like a fin stack that we would see in like a laptop. We simulated this, that does seem to kind of work. So we got that made. And we stuck with this design like all the way from Rev C to Rev F. It caused so much problems. So one of the issues you have is that you really need the surface contact between this plate and the 845 to be as flat as possible. So we designed this to be on spring screws. But you can see in that picture, like the spring screws are way too big and nobody really makes the smaller ones that we needed. So then we got custom screws made. Okay, the custom screws, that looks a lot better. But then like the fan standoffs, like do you really want to put like all the screws in and like it has like little like capped on labels on there that get everywhere in production. So we designed custom standoffs for the fan. We figured out like, oh, we need to optimize the intake path. So then we added like a big hole in the front of the case. We put like an extra fan on there and it just turned into this whole big mess. We even came up with this monstrosity at some point because we figured out that like one of the fin stacks just wasn't quite long enough to like be super efficient. So we like doubled the fin stack up. We added backside cooling. We added a fin stack in there. It just didn't really, like we could kind of get it to work somewhat on a 3x level in this form factor. But also right around this time, we figured out that the GPS performance wasn't actually quite what we hoped for. Like if you look on this graph, like the bottom line, that's the horizontal accuracy that a 3x would get on a route. And the one on top of there, that's one of the early production, early prototype Mises that we built. And it's just a lot worse. So that turned into a whole thing as well. One of the most annoying things is that the 845, because it's like, it has so many sub-blocks and it runs at so many different frequencies and PLLs, that it outputs harmonics basically like in the whole broadband spectrum around GNSS. So you really need to shield it. Like on the 3X, it's like nice, it has like its own shield, it's like covered by the heatsink, like that kind of works. But for this, I mean, we designed in a shield. That helped a little bit. Turns out like the heat pipe, because it's not mechanically connected, because it's on spring screws, it's not grounded enough, so we like tried grounding that. That kind of helped. We covered up the whole thing to like cover any holes. That kind of helped a little bit. Then we had to add like shield, like a foil under the holes. Another small improvement. We had to add like a bottom side shield. It just turned into this whole thing. At some point, we even got like production versions of like the shields that we would like get the machines to solder onto the boards. Because they're like an awkward shape, they like would bend and like warp in production, and then sometimes like not all the edges would get soldered, so that also like became somewhat flaky. So we ditched that and we went to like a full like unibody copper thing that sat on top of that, like sacrificing some of the thermal performance for RF. And still, you would get like plots like these that didn't quite match what a 3 or a 3X could do. Another issue for GPS performance that we had was that some of the signals that are just like happening in the device, like driving the display or like driving the cameras, they're at certain frequencies that are like, if you multiply them by an integer amount, you would get harmonics that are right in the center of GPS frequencies. And GPS is an extremely low amplitude signal. So it gets drowned out by basically anything that's even close to it. You can see this on these plots. Like Maxime wrote this very nice piece of software that would like turn off the screen, turn the screen back on, turn the cameras on, turn the screen back off. And so like from this graph, you could see like, okay, the screen has a big effect, the cameras have some effect. And some of these you could just fix with software. Like we just looked into like the display code, and we could change like the frequencies the display was running at. We changed like drive strengths of certain like regulators and the 845 firmware. Like it turned into this whole hassle to get something to like barely work. Another thing limiting GPS was just that the antenna was on like the edge of the board, and the antennas, like these patch antennas, are not designed to do that. Like they're designed to be in like a perfect vacuum with like a nice 10 by 10 centimeter ground plane that's like very nicely centered, which is just not possible in the form factor that we were building. This is another RF plot. This is because the antenna's on the edge. Like You want this blue trace, which is what you measure. You want that to be in the middle to like be more efficient. Won't bore you with all the details, but that took a whole bunch of like optimization as well. But that then changes like the resonance frequency of the GPS, so then you have to go to like brute force all these values. This literally took months to get something that's like barely on the level of a 3x. But in the end, we kind of got there, like on RevF, C, D, E, F. We got to like something that somewhat matches a comma 3. And it's okay, it's maybe barely shippable. But if you just zoom out a little bit, we had this RevF that like barely worked thermally. We had barely working in a GPS. The case was still metal. It would get like uncomfortably hot. The fan had to run now because we didn't passively cool most of the chip anymore, which is kind of whiny. The shielding is like, there's a lot of custom components to like barely make it work. And we just came up with just, we'll do one more redesign and completely solve all the issues like just fundamentally. And that's how RevH came to be. And that's remarkably close to what we are actually shipping now in RevI. So it's, as you can see, it's like a complete redesign again. Like the 845 moved back to the bottom side of the board. We ditched the big fan hole for the blower, which allowed like a lot more space to lay out the components all very nicely. This also added the space to like add this exposed ground path, so you can have like a shield that fits nicely on top of it. The shield could also be like the heatsink, we figured out. And then from the backside cooling, it turns out that you can just have a copper plate here, and that's high conductivity enough to like just conduct that through the posts back into the bottom heatsink. And this just turned out beautifully. Even the GPS is like somewhat more central into the board, and that just fixed so many things. So this is you've already seen this, but this is the heatsink design we came up with. This is also the integrated shield, and it just is great. After that, we still did a whole bunch of experimentations on the input design, like the airflow input design. A lot of these had trade-offs between like noise production and thermal performance and looks. So we literally built like hundreds of these. The team also optimized the thermal design on the heatsink side. So it turns out if you add like a nice little cover over the heatsink to not recirculate air, and also to cover the sides of the fins, you would get both better thermal performance and lower noise profile, or at least like shift the frequencies away from the noise profile so you barely can't hear it anymore. And that was a massive improvement as well. Even more intake designs we tried before finally ending up with what we're shipping. And like thermally, this is what we ended up with, which is honestly quite incredible. Like if you look at this graph, like the blue line, that's the comma 3x. So it's running a constant like 6-watt load. And then we just sweep the fan power, wait until it settles, and you just see whatever the CPU temperature ends up in. That's, the 3x, it works pretty well, but it's thermally not the best thing in the world. So in RevF, like the final design that we had, like if you run the fan like at 60, 70%, you could somewhat get close, and it's probably good enough for what we wanted to do. And then if you go back to like this abomination, like the heat sinks on the back and like the extra fin lengths and stuff, you could get it to be somewhat better than a 3x. That's the green line. And then the RevH design, that's in like a league of its own. Like even at like 30% fan, it just like blows the 3x out of the water. And this obviously also translates into driving performance. Like this is just a log app from like a route that we drove on the RevH. Like loaded while driving, like regular openpilot load, the CPU barely like dips above 50C, which is quite incredible. Because it's also under the 75C that we try to control the temperature at, the fan was basically not running at all. And then for GPS performance, that doesn't look any different than a 3 or a 3X. So we also completely solved that. Of course, like you can't do all the experimentation in-house, like all the test setups you build, like you're only testing like one device, you test it for like one time. But if you wanted to get some data on like what this thing would perform like in the field, like what are the 1% failures like, then you really need to like just get so many driving hours on this thing. And we had this nice group of people that we trusted to not leak the device. That we sent some devices to. They got like the unbox experience, they got to test the UI, provided a whole bunch of feedback. They racked up tons of miles on this device, which really makes us confident that it's a very solid design. Other than that, we have testing infrastructure from the other teams as well. So I already showed you this. This is like a testing dashboard that Maxime from the openpilot team built, which is very valuable. It just shows like every MISI drive of every day. And you just look at like all the sensors that we have in the device, like see if there's anything wrong that you don't expect. This slide's somewhat outdated apparently, but that's like the amount of segments that we got driven around RevH. And then we also had like the green check mark every day from the autonomy team, which basically meant that, okay, all the data, all the logs that we gathered from the device were actually trainable, which also is a very strict check to make sure that all the sensors and the cameras and stuff looked good. After you've done all of that, you're still not done. You still need to send it off to certification. So they put in like this big anechoic chamber. You run your standard openpilot loop, and then they just measure like whatever RF frequencies come out of it. The limit is red line. This stuff, that's all noise. That's all like the cabling and the power supplies and stuff, so you don't really look at that. But like, look at how flat this line is. Like, this is basically just background radiation. Like, the shielding we did on this thing is just incredible. Like, I haven't seen any other device that looks like this. We also went to Shenzhen. I think Adeep already showed some of these pictures. This is invaluable feedback. Like, this is so valuable that you can see like how the processes are being done, so you can like incorporate it into like the next revisions, like make sure that it's super easy to produce. You don't get any defects in between batches and stuff like this. Like in the right, there's like the general flow of how to produce like a MISI heatsink or comma 4 heatsink, where you start with like extrusion, they mill that in a few steps. It's just so valuable to know how all these things do. That's not only the device performance that improved quite a lot, it's the complexity of these things. It's just so much reduced from the 3X. Like, I went through like the list that we have, and like the unique BOM items, like the bill of materials on this thing, that's almost dropped in half from the 3X. The amount of process steps that we do in-house, like the assembly steps, like focusing lenses, sticking on tapes, like plugging in cables and that stuff, that's literally halved. And the amount of custom parts, where we actually design it instead of just buying it off the shelf from different vendors, that has more than halved. So this is quite an incredible achievement, I think. If you don't believe it, then it's way easier to build. I mean, we have a booth over there. Just go up to it, take a look at the components, put one together yourself. You don't need any training. You can literally do it in a few minutes. So I think that concludes most of what I wanted to talk about. I think we finally got to a design that's worthy enough to be called the comma 4. That was it.
Thank you, Robbe. We have a couple minutes for questions. Any questions for Robbe?
Do you guys do any formal vibration testing, or is it just relying on the ones in the field is working?
We mostly rely on the field for that, yeah. We've thought about like making like a vibration setup, but we haven't just gone around to it to figure that out.
You know, just like you have the SMT line in-house, and that really helps with iteration speed, would you ever consider bringing like the machining in-house or molding, injection molding in-house?
We'd absolutely love to. Like, if we could get CNC parts like by the end of the afternoon, that would be amazing.
Okay.
The office that we have now is just not quite set up for it yet. Like, we would need like a decently sized like actual factory building for this, but hopefully in the future, yeah.
I try to fit as much in our office as we can, but sometimes there's a stretch.
How do you find your simulation tool relative to the testing that you're doing? Is there any opportunity that you get to improve the simulation tool that you're using?
I already had this conviction, but I'm getting more and more convinced that like most of the simulations we do are just not very useful. Like, like you've seen this, right? Like we've simulated so many things that you just, even if you like get like one very small detail wrong, the conclusions that you derive from this are just, they're just not useful. Like, just spend like the 2 days, build the thing in-house and just test it.
Is moving to Raylib and CPU rendering going to make a measurable difference to your kind of steady state CPU load / temperature?
Hopefully. But I think the problem is like every time the openpilot team makes any improvements on this, it's just all eaten up by autonomy again. So you just run bigger models.
All right. Thank you, Robbe.